Okay, welcome to the third video for the Psychometrics Refresher course. And in this video, we're gonna talk about dimensionality, or basically we're gonna focus on factor analysis. In the previous video about validity, I mentioned that part of construct validity is checking whether the dimensionality of your measurement instrument matches your theory, and that's something that we check with factor analysis. And in this video, we're gonna take a slightly deeper look at that. Alright, now, when we're doing a factor analysis or where we're checking the dimensionality of our measurement instrument, there's basically three key questions. The first question is, how many dimensions are there? The second question is, if there's more than one dimension or more than one underlying factor, do we think that those dimensions are correlated or not? And then finally, what actually is the meaning of these dimensions? Now I'm going to move on before going back. For the first question, the number of dimensions, that can be based on theory. So let's say that we made a multiplication test where all the equations that people have to do is multiplications. Then you could say, okay, based on theory, I'm assuming that there's one underlying factor, the factor multiplication ability. Or, for a slightly more realistic probably example, let's say that we have an ADHD questionnaire or an ADHD measurement instrument. We know that part of ADHD consists of attention deficit. We know that part of ADHD consists of hyperactivity. And we know that we have questions about both, right? So remember, another part of validity is that the content of your measurement instrument matches the construct you're trying to measure. So for a good, valid ADHD questionnaire, we need to have questions about both attention deficit and hyperactivity. Now, based on the theory about ADHD, it makes sense to think that in this case, 9 items of our ADHD questionnaire should load on 2 factors, right? They should load on an attention deficit factor and they should load on a hyperactivity factor. So then here, based on theory, we would expect there to be 2 factors. Might be an overall factor above that, ADHD, but the items load on 2 factors, attention deficit and hyperactivity. Now obviously, I'll go back to the first slide, we don't always have theory to guide us, so then we can also use an exploratory factor analysis, and then the number of factors or the number of dimensions is determined based on 4 sources of information, basically all using the eigenvalues. So we're going to look at eigenvalues, script plots, etc. Alright, now, how do you determine the number of dimensions? Here we go. Based on eigenvalues. And what were these eigenvalues again? Well, as we said during the course, don't worry about the eigenvalues too much. The eigenvalues basically are an indication of how much of the total variance is explained by an underlying factor, but you don't have to worry about that too much. The thing that we're going to use eigenvalues for in the course and also during the course exam is determining the number of factors that are at the heart, basically, or underlying our measurement instrument. Now, I already mentioned that this is what you do if you don't have any theory. If you have theory, then in practice, I would always say, please use that as a guideline. Having a strong theory is always better than doing stuff data-driven, but sometimes you have to, and during this course, we're going to focus on the data-driven part as well. Alright, now, as I said, there are several different ways, 4 in total, so theory, variance explained, eigenvalue, so Kaiser criterion and script plot, but the last 3, so the variance explained, the Kaiser criterion and the script plot, basically all use eigenvalues. They just represent the eigenvalues or display the eigenvalues in a slightly different way, but they all use the same information. The variance explained criterion, basically what that does is it checks the percentage of variance explained. It checks where the differences between successive factors in percentage of variance explained becomes smaller, and says, okay, if the increase in explained variance from one factor to the next isn't that large anymore, stop, basically. So in this example, we could say that the first factor explains 63%, the second factor explains 9%, and then after the 9% it goes to 754. So differences here between the 9 and the 7, and the 7 and the 5, and then the 5 and the 4, differences here aren't as large compared to the drop in explained variance from factor 1 to factor 2, right? So from 63 to 9, huge difference, and compared to that huge difference, 9 to 7, not so important, 7 to 5, not so important, etc., etc. So based on percentage of variance, here I would say, okay, you know what, one factor will probably be enough. The second way of checking how many factors you need to use is the so-called Kaiser criterion. It's the easiest one to use. It just looks at the eigenvalues themselves and says, as long as a factor has an eigenvalue larger than 1, include it. So that's looking at this column instead of the percentage of variance explained column. So the Kaiser criterion uses this. Well, there's only one eigenvalue here that's larger than 1. That's the eigenvalue for factor 1. So the Kaiser criterion would also say use one factor. And here you can clearly see that both using the explained variance and the Kaiser criterion are basically doing the same thing. We either look at the eigenvalues themselves, or we look at the eigenvalues after we transform them more or less into explained variance. But it's the same thing, more or less. Right, and the final non-theory based method of determining the number of factors you need to use is the scree plot, which is at the bottom left right here. The scree plot is just a plot of the eigenvalues, so these values of 5.684, 0.893, 0.668, they are all plotted here, with the eigenvalues on the y-axis and the number of factors on the x-axis. To use the scree plot, we basically look for the point of inflection, which is a fancy way of saying we're looking for the elbow, more or less, of the scree plot, which would be over here. Steep decline, more or less horizontal plot after that, so the inflection point in the elbow is here at 2. And using the scree plot, the idea is what you should do is look for the elbow point and use one factor less. So here it says the inflection point is at 2, so we should use one factor. And again, you can see that since this is all based on eigenvalues, basically what we're doing here is we're again looking at differences in the percentage of explained variances from one factor to the next. So like I said, there's a huge drop from 63 to 9, and then from 9 onwards the differences are relatively small. Basically I'm doing that here as well with the scree plot, but I'm using it visually. So I'm not looking at the numbers, I'm looking at the plot. It might be somewhat easier, but again, it's basically the same thing. So to sum up, if you need to determine the number of dimensions, if you have a theory, great. Theory is always best. If you don't have a theory, you can do data driven, you can do exploratory factor analysis, and then you can use the variance explained by the factors, the eigenvalues, so the Kaiser criterion, or the scree plot to determine the number of factors that are underlying your measurement instrument, or seem to be underlying your measurement instrument. Alright, now that's a good start. Right, so we determined the number of underlying factors, which is great. Now think back to reliability. When we were discussing reliability in the first video and the second video, I said that reliability is all about, am I measuring the same thing over and over and over again, which is important, but it wasn't enough. Because when we got to validity, I said, yeah, reliability is nice, knowing that you're measuring the same thing over and over and over again. But the fact that you're measuring the same thing over and over and over again is no guarantee that you're actually measuring the thing that you want to be measuring, right? That's where validity came in. Validity makes sure that you're actually measuring what you want. Now, same thing basically goes for factor analysis. It's nice that we know that there's like one factor or two factors underlying our measurement instrument, but we're not 100% sure yet that it's the actual factor that we're expecting, right? So think back to the multiplication example that I gave, the multiplication test with the one underlying multiplication factor. It's nice that there's one factor underlying that measurement instrument, but am I 100% sure that that one factor is the factor multiplication ability? Or when we move on to the two-factor example with the ADHD test, I was expecting two factors for the attention deficit and the hyperactivity factors. Great if I find two factors, but am I absolutely sure that those two factors are the attention deficit factor and the hyperactivity factor, or two different factors with completely different meaning? I don't know yet, right? So determining the number of factors isn't enough. We also need to figure out what they actually mean. what the interpretation of the vectors is. And to do that, we need to look at the vector loadings. So the vector loadings are our gateway, so to say, into the meaning of the vectors. Because what we're going to do is we're just going to check the vector loadings of each item on all the underlying vectors, and based on what item belongs to what vector, we can come up with an interpretation of that vector. So that's an complicated way of saying. So let's say I'm looking at this test over here. I see that the vector loading for item 1 on vector 1 is larger, clearly larger, than the vector loading for item 1 on vector 2. Doesn't matter whether it's positive or negative, I'm looking at the absolute value. This value is clearly larger than this one. Item 2 also clearly belongs to vector 1. Same for item 3, item 4, item 5, item 6, item 7, item 8, and item 9 here. This is a bit of a weird example, but go with it. Now the thing is, what I'm looking at is I'm looking which items belong to which vector. Then I look at those items, and I'm trying to figure out whether there's an underlying theme in those items. So let's say that, if I go back to my ADHD example, let's say that I found two vectors, I look at the vector loadings, and I do indeed find that the vector loadings for item 1, item 3, item 5, and item 7, for those 4 items, the vector loadings for vector 1 are clearly larger than the vector loadings for vector 2. So I'm going to say, okay, 1, 3, 5, and 7 belong to my first vector. And that the vector loadings for item 2, 4, 6, 8, and 9, for those 5 items, the vector loadings for vector 2 are way larger than those for vector 1. So I'm going to say, okay, 2, 4, 6, 8, and 9 clearly belong to vector 2. Right? I don't know that this is hyperactivity yet. Don't know this is attention deficit yet. I just know 1, 3, 5, and 7 belong to vector 1. 2, 4, 6, 8, and 9 belong to vector 2. Alright, great. Then I'm actually going to look at those items. I'm going to say, okay, so item 1, I don't have enough attention to detail at my work. Okay, great. Item 3, I make sloppy mistakes in my work. Okay, so clearly some attention to detail already coming up. Item 5, when I'm doing something, I find it hard to keep focused. Okay, that also seems to be implying some issues with attention. And finally, item 7, I'm quickly annoyed. Right, that's less clear, but overall, looking at all 4 items, there's clearly some attention-based thing going on in item 1, 3, 5, and 7. And that makes me think that vector 1 has an interpretation that has something to do with attention. Okay, then moving on to vector 2. So let's look at item 2. When I sit, I fiddle with my hands and feet. Alright, so that's difficulty staying still, basically being a little bit high energy maybe. Include 4 as well. I rock the chair back and forth. Yeah, alright. Item 6. I feel restless. Yeah, there's a clear pattern of a hyperactivity coming up. So item 8. Constantly busy like I'm driven by an engine. And 9. I keep on talking all day long. Yeah, this is clearly has something to do with hyper or overactivity. So that makes me think, looking at the description of item 2, 4, 6, 8, and 9, that vector 2 has something to do with over or hyperactivity. And based on those items, I just determined the conceptual meaning of both vector 2 and vector 1. Here I'm also helped by theory, obviously, because I know it's an ADHD questionnaire, but I really use the wording and the content of the items to figure out what those vectors could be. Alright, now, moving back here. I already said this is a bit of a weird example, right? Because all the vectors or all the items here appear to be loading the most on vector 1. So if everything appears to be loading the most on vector 1, why did I extract 2 vectors, right? I did that on the criterion on the previous slide, so I used the Kaiser criterion, discrete plot, eigenvalues, etc. And I figured out there should be 2 vectors. But then when I'm looking at these vector loadings, it's not that easy to figure out what those vectors mean yet, because everything appears to be going to vector 1. This is an extreme example, sometimes there's like 1 or 2 going to vector 2 as well, but it's not easy to see a pattern here. And that's because we haven't rotated yet. And rotated was probably one of the most abstract, vague things we discussed during the course. And rotation has to do basically with figuring out from what abstract point in multivariate space, I'm going to get back to this, you could have the best view of the vectors underlying your measurement instrument. Basically, it comes down to you want to take a picture of some scenery and you figure out where you need to stand to get the most complete overview of the scenery you want to have. So maybe on holiday you want to have a picture of both the Eiffel Tower and your girlfriend, and you need to figure out how to position yourself to have both the entire Eiffel Tower and your girlfriend in the picture. Basically, rotation is doing the same thing but with vectors. So where do you need to stand to get the best view of both vectors? Now there's a mathematical thing that goes on then. Basically what we do is we take an x-axis and a y-axis and we rotate them a little bit to make sure that all the items either clearly belong to vector 1 or clearly belong to vector 2 in this case. So basically we go from this, are all items have high loadings on vector 1, and all of them have, remember looking at absolute values, more or less the same range of values on vector 2. They're all between 0.4 and minus 0.4, so the absolute values are more or less the same. So we can't really distinguish them there, not really clear distinction on vector 1 either. So what we do is we shift this y-axis and x-axis like so. And now the distinction becomes way clearer. Now these items have pretty high values on vector 1. These items are near 0 on vector 1. And these items all have low scores or pretty low scores on, pretty high scores on, let me redo that. So these items all have pretty low scores on vector 1. As you can see, even I sometimes still get confused by rotation. All these items have low scores on vector 1 because the vector 1 scores are now down here. So they all have vector 1 scores around 0.2 or 0.3, while this cluster of items over here has really high vector 1 scores around 1. Similarly, these items over here have pretty high scores on vector 2, the y-axis, all 0.5 or higher, while this cluster of items down here has a maximum vector 2 score of 0.2. So here you can see that the distinction of scores on the two vectors for the items is way clearer than it was when we were looking like this. So after rotation, seeing a clear pattern in which item belongs to which vector is way easier, which is important because as we saw earlier, we need those vector loadings and we need to have items that clearly belong to one vector or another to figure out what those vectors mean. Now rotation is abstract, don't worry about it too much. Just remember that you can do it, you don't change anything weird about your data, we just do it to get a clearer picture of what a vector actually means. So rotation is basically getting a better vantage point and getting a better overview of the vectors that you have in your data. Okay, now this rotation is related to the second question we need to ask when looking at vector analysis and when testing dimensionality. And that second question was, if you have more than one vector, do you think those vectors are correlated or not? And we basically discussed two types of rotation during the course, orthogonal and non-orthogonal rotation. And that had to do with the answer to that question. If you think that your vectors are unrelated, so uncorrelated, and what you're going to do is you're going to do a non-orthogonal rotation, which means that the x-axis and the y-axis, or the vector 1 axis and vector 2 axis, whatever you want to call them, have an angle of 90 degrees between them. So basically they're the normal axis layout that you know, 90-degree angles between the axes. That means that vector 1 and vector 2 are completely uncorrelated. That would be the Varimax rotation. Now in social sciences, that's probably not the most realistic assumption. In social sciences, everything is related to everything, so it makes sense that your variables, your underlying vectors would also be correlated, right? So hyperactivity and attention deficit are also really likely to be correlated. If you want to allow your vectors to be correlated, then what we're going to do is a non-orthogonal rotation. Right? So the Varimax was an orthogonal rotation. We assumed that the vectors were uncorrelated with each other. And what we call the Obli-Min rotation is a non-orthogonal rotation, and we're assuming that the vectors can be correlated. Right? So the terminology is, again, unfortunately, statistics terminology, so not really clear, but orthogonal means independent of each other, 90-degree angle. Non-orthogonal means dependent or correlated, and that means that the axes don't necessarily have a 90-degree angle between them. And like I said, the orthogonal one, so the uncorrelated vectors, that was the Varimax rotation that we used in SPSS. And the non-orthogonal one, so the one where vectors are allowed to be correlated, that was the Obli-Min one. Alright. Now, the thing is, as I mentioned, we needed those vector loadings to figure out what the vectors mean, right? And we want to look at vector loadings after rotation, because after rotation it was easier to see a pattern. However, depending on the rotation we use, we get different sets of basically vector loadings, or at least vector loading information that we can look at. So depending on whether we did orthogonal, so non-correlated vectors, Varimax, or non-orthogonal, or correlated vectors, Obli-Min rotation, the output that SPSS gives us is different, which is slightly annoying. This is especially important when we're using the non-orthogonal rotation option. So when we're looking at correlated vectors, we need to make sure that we're looking at the correct information in the SPSS output. When we're using orthogonal, when we're doing Varimax, the number of tables is less than the number of tables we get with correlated vector rotation, and then it's quite easy to see that you don't have that many tables in your output. But when you're using rotation, you get a set of tables, and not all of them are equally interesting. And I'm going to be focusing on two of those tables that you get in your SPSS output. We're going to look at the structure matrix, and we're going to look at the pattern matrix. Now, the structure matrix just gives correlations, right? So they take the scores on vector 1 for everybody, they take the scores on, let's say, item 7 for everybody, and they just calculate the correlation between the two. Those correlations are what you get in the structure matrix. And we get it for each item and each vector, each combination of the two. Now, interesting information. However, it might still be difficult to see a clear pattern in that structure matrix. It could still be difficult to see a clear pattern in what item belongs to what vector. Now, fortunately, next to the structure matrix, we also get a second matrix called the pattern matrix. And this pattern matrix, this one contains the actual vector loadings. And these vector loadings, instead of looking at the correlations, they give the unique contributions of a vector in an item. So basically, what we see in the pattern matrix is more like regression coefficients. And remember, correlations gave total overlap between two variables, for example, an item and a vector, while regression coefficients and vector loadings give unique overlap. So if we move to the Venn diagram, what we see in the structure matrix, for example, for vector 1 and item 1, so the 0.781 correlation, is the total overlap between the green circle representing vector and the blue circle representing item 7. So the total overlap is what we see in the structure matrix. Same for vector 2. What we see in the structure matrix, the 0.576 is the total overlap between the green vector 1 circle and the red, between the blue item 1 circle and the red factor 2 circle. So the 0.781 correlation between item 1 and, oh sorry, this is item 7. This wasn't a really helpful example. Let me do this again. So in the structure matrix, like I said, we have correlations. So we have the total overlap, and this was about item 7, so let me rephrase this. So in the structure matrix, the correlation between item 7 and factor 1, so this 0.891, what we're looking at is the total overlap between the green factor 1 circle and the blue item 7 circle. So the total overlap between green and blue is the 0.891 in the structure matrix. Similarly, the 0.725 that we see for item 7 and factor 2 is the total overlap between the blue circle for item 7 and the red circle for factor 2. So the total overlap between factor 2 and item 7, the correlation between the two. What we have in the pattern matrix, where we have the unique contributions, the factor loadings, is not total overlap, but unique overlap. So the 0.805 that we have for item 7 and factor 1 in the pattern matrix is that part of the overlap between the blue circle and the green circle where there is no overlap with the red circle. So only overlap between blue and green, no red. So the piece in the middle where green, blue and red overlap, that part is not taken into account in the pattern matrix. Same for the 0.112 that we have over here for item 7 and factor 2. That's the unique overlap between the blue circle and the red circle, where there is no overlap with the green circle as well. Now, usually the structure matrix and the pattern matrix can both give a clear pattern, but sometimes when the structure matrix doesn't, the pattern matrix still does. So it's important to look at both to figure out what the pattern is of items belonging to which factor. Alright. Well, that was it for this third video on dimensionality or factor analysis. 2 more to go, and then maybe some additional videos depending on what questions came up during the refresher tutor groups. But next time, in the next video, in video 4, we're going to be talking about bias.